within this webinar. And the presentation will be given by Dr. Jinjun Jin from Shanghai Jiao Tong University. And the topic he will be addressing is on resilience-informed integrity management of offshore wind farm systems. I've had the pleasure to know Jinjun since quite a number of years. So we are talking about actually almost 20 years, I think. It's getting very close. And Jinjun holds a PhD degree from ETH in Zurich. And right now he's an associate professor at Shanghai Jiao Tong University. And he has been in this position for more than a year, almost 2 years, I think now. His research interests are quite wide in probabilistic systems modeling and analysis using both bottom-up traditional approaches, but also here within the last couple of years, more data-driven modeling and analysis, looking at catastrophe modeling in the context of applied decision theory and life cycle analysis for infrastructure systems. And in this, he's also using AI technology and Bayesian approaches is really the backbone of his research and developments. His proliferate researcher within just the last couple of years. He has more than 50 academic papers, and he's been so good that 2 of his journal papers have also been chosen as best papers, and one is a featured article. In 2013, he was awarded the Hoyat Daly Award for Innovation in Computing by Wiley, and received Chinese government awards in 2013 and 2012. So, Jinjun Jin, we look very much forward to see your presentation, and remember that after the presentation, we would like to give the audience the opportunity also to ask some questions. And so we are looking very much forward to this, and please do ask questions. We would like to have a dialogue. Jinjun, the word is yours.
Thank you, Michael. Hello, everyone, and it's my honor to have this opportunity to have this presentation actually on this webinar. And thank you all of you that you attend this my presentation. I'm looking forward to your feedback and comments. Actually, I'm currently working in Shanghai Jiao Tong University, and the topic of my presentation actually is, as Michael already introduced, is resilience-informed integrated management of offshore wind farm systems. As you all know, you may know that offshore wind farm systems actually are hot or popular topic recent years, but the integrated management of such this typical large scale, but also complex systems are challenging. And the idea here is that we propose a resilience modeling to enhance or support this integrated management, such as like the decision in design and also operation and maintenance activities, and such and this and the storekeeping and these things. Yeah, so that's the overview of this presentation. Yeah. Sorry. Before I start my presentation, actually, I would like to introduce, actually, we have a good, also strong team on this topic, integrated management of offshore wind farm systems. Actually, I started this some years ago when I worked together with Michael at his research group at Aalborg University on this wind farm systems. There, I also met Miss Ming Liu and Dr. Wei Hen Zhang some years ago, also in when during their stay in this Aalborg University. Both of them actually come from the group of Professor Dagang Lu from Harbin Institute of Technology. And also in Denmark, we work together actually close with Dr. Johnson Zhu. Actually, he is engineer and also executive assistant to CEO of the Shanghai Electric Wind Power Group European Innovation Center. EPS is a company in this located in Aarhus, city of Aarhus in Denmark. Actually, we all work close each other on this topic, and it's very interesting. Although it's a complicated problem, but it's also meaningful and interesting topic, I think. And we work close together several years now. Even we are located at different countries and different cities, but we still actually work hard on this topic. Yes, that's here the slides list the content, the main contents of my presentation. Actually, the first I would like to introduce the motivation, actually the challenges and the potentials of the integrated management, and also I would present this the difference, not the difference, the evolution of our knowledge or our understanding of the performance of engineered structures. So from 4R is from reliability, risk, robustness, and resilience. And then after that, I present briefly about the resilience modeling and the resilience informed management. Actually, most of you may already get some idea from the first presentation from Professor Faber's this presentation on this webinar. And then after that, you may see that we need the basis for this resilience modeling and the resilience informed management actually is the accurate or the correct on the system representations. I would like to introduce or present briefly about this system representations on these offshore wind farm systems. Then after that, I would like to introduce or illustrate the examples we have for this framework. And then after the end, some conclusions. And finally, I would like to briefly introduce and present shortly this ongoing research at my research group at the Shanghai Jiao Tong University. Yes, that's the map of the contents of my presentation. Actually, offshore or wind farm systems actually is more and more popular, as you may already know that the right side, at the right corner, there's a figure recently published by Wind Europe, shows that the plan, the new onshore and offshore wind installations in Europe in 2021. Yes, so yeah, you can see that the wind farm actually become more and more important. Actually, when you read the news recently, following the conflicts between Russia and Ukraine, Germany, Denmark, and UK, they focus much more on these wind farms, especially on offshore wind farms. So they are more and more important, especially on this energy production. Yes, but considering our main concern on offshore wind farms, there's safety and their service. You can imagine that's different with the typical civil buildings or civil engineered structures. The main difference is that our main concern on such large-scale industrial systems like offshore wind farms, if we trade off between this service, compare the importance of service and safety, we would see that the safety is not as important as the service. Our main concern actually is the service of offshore wind farms instead of safety. Here, I just list some words or terms included in this service. Service is a big, I think, term. You may, a general term that actually the safety, the benefit, and also the energy provisions, all these things are included in these services. And our expectation actually is to develop resilience-informed integrated management to enhance these services. It's not only the total service, but also the service fluctuations during the service life. That's our the expectation or our aim for this research also. And following the main concern, the evolution of the main concern on such typical large scale and important industrial systems, industrial engineering systems, actually our knowledge or our assessment on the performance of such systems actually evolves in the last years. At the beginning, in the beginning of 1980s, or even the end of 1970s, actually we start to use reliability to assess performance of engineered structures. The reliability is easy to understand from the word, because reliability we consider resistance of the structures and also the load of the external loads of the engineered structures. So we use, for example, R to represent the resistance, and we use S to represent the load of the external load of these structures. Then the probability that resistance is no larger than external load, then it means the structural failure. And the probability of structural failure is the failure probability, and the 1 minus the failure probability is could consider as the probability of safety of the structures. So that's the definition of reliability. It's even now it's the main measurement of the structural performance. Then after some years, we present the concepts or the idea of risks. In these risks, you can see that we not only include this probability, but also we introduce the consequence of the events or the disturbances. So we multiply this probability of the occurrence of the event, and with this the consequence of these disturbances. Then this is the expected value of the consequences of this disturbance event, and the sum of this n event we considered, and disturbances we considered, then it's considered as the risks of these structures. And then around 15 years ago, if I remember correctly, this JCSS, Joint Committee of Structural Safety, presents actually the concept of robustness of engineered structures. Actually, this is the figure I copied from JCSS report. Actually, when there are some external exposure or disturbances or hazards of some engineered structures, then there's a vulnerability. Vulnerability actually measures the direct consequences compared to the total consequences. The direct and the indirect consequences, the ratio. And then there's not only direct consequence, but there are also indirect consequences or follow-up consequences. Then the terms, the word robustness comes up or emerges. There's two possibilities. One is there's a system damage states, but also like functionality events of the functionality loss of the structures. So we can consider as a follow-up or indirect consequences. You may already get the idea from past presentations, and also you may already get the idea from the report of JCSS that the direct consequences and the ratio between this direct and the total consequence CT of given some scenarios or given some events is considered as the robustness index of the engineered structures. So that from the risk, we consider consequences, but the robustness, we divided consequence into direct and indirect consequences. So it's one more step more. And now, recent years, around 10 years or even more years ago, in the field of engineering, field, we presented the resilience concept. The details of this concept actually already discussed in the first presentation by Professor Michael Faber. One typical definition is resilience is a system ability or system own ability to plan for or recover from or adapt to external or disturbances, adverse events over the lifetime, actually. So that's the main idea. Actually, the reliability, risk, and the robustness concepts you may find in this lecture notes here, this risk and safety in engineering published by ETH, sorry. And there's challenges actually to consider in this integrated management of these wind farms, especially these offshore wind farms. For example, these wind farms are increasing in size and increasing in this complexity, especially in these offshore wind farms, because offshore wind farms is far away from people's activities. So normally it's a big size, but big size and large complexity makes also the challenges. You may find that the world's first energy island, actually it's already built in North Sea in Denmark. Now I think currently it's a 3 gigawatt. It's capacity, and it can support 3 million families using these electricities. And the news says that in around 10 years later or 20 years later, it will develop or extended to 10 gigawatt and support 10 million families. So you can imagine that the big size and these complexity problems, because it's far away and it's very difficult to do this operation, O&M, this and maintenance activities. And the second problem actually is because of this importance of these wind farms, actually this societal vulnerability actually with respect to disturbances increases. And we need actually sustainable developments, but that the need calls for improved these integrated management strategies. Decision support actually for safe, resilient, and efficient design and integrated management actually must be enhanced. That's the challenges or the whole idea motivation of our research. And some main problems still there. The first is the system effects. Actually, you can see from my following presentation that wind turbines and wind farms actually is a typical component, subsystem, and system problems. So there are strong system effects we have to consider across these components and subsystems. But normally, in this analysis of large-scale engineered systems are neglected or simplified. And dependencies actually is one main indicator of this system effects, especially in these failure modes across components and subsystems are not fully accounted. We hope to fully account this in our framework. And then apply this, we need to apply, well, we have to apply actually these target reliabilities for the performance of components and the subsystems. And have to optimize them jointly and balance with the consequence of failure consequences. Yes. And here is just for illustration purpose, we show that there are different levels for dependencies within a given wind farm. So there's wind turbines in these wind farms. And inside each wind turbines, there's mechanical subsystems, there's electrical subsystem, and there are also structural subsystems like tower or blade. And these subsystems, they are actually interconnected. So they have dependencies in the performance during their service life. And there are totally n or many wind turbines in one wind farm. And these wind turbines actually subject to common wind fire and common natural hazards and even common operational load. They are also influenced or controlled by same common this management level and decision makings. So they hold by same person or same decision makers during their service life. So it's the dependencies of wind turbine levels. So there's different levels actually in this in one wind farms. And if we consider the systems, the wind farms as a system. Actually. So another two problems that we would like to point out is that the capacities and the abilities supporting the system recovery, like economic capacities, management abilities, which actually they are actually critical to the resilience performance of the system, they actually change over time. So they are time varying. And the last is the framework that can be directly implemented with the modern techniques and tools commonly applied in the industry is missing. Actually, as we show on the post of my presentation, that the aim of our work is to actually present the resilience-informed integrated management for offshore wind farms, not only from theoretical perspective, but also from that practical practicability that perspective of that. So we hope that can directly implement it in the industry or in engineering practice. That's the and that there are two potentials, or there are two potentials that why we can realize as that at present time step for this problem is the first is actually, as we already showed in the previous slides, for example, like some international organization like JCSS or many research groups in all over the world that already present these integral system representations and decision analytical frameworks for these integral system representations and already formulated, already available. And as you can see from the former figures in one side, that the probabilistic modeling of system characteristics, like for example, vulnerability, robustness, and resilience, they are already new insights, and such new insights enhance decision support with respect to design, O&M, etc. Yes, that's the two potentials. Yeah, okay. All I presented in the past slides are the motivations. Now I would like to introduce the whole idea of this resilience of systems using some illustrations to do that. So here, this is the figure which shows that the fluctuations or the variance of benefit or of some wind turbine or some wind farms during the whole service life. So they are time varying curves actually, and when they are okay or they are perfect in good state, then the service state is okay and it's stable here for benefit and the reserve. And after some time, for some days or some months or some years, there's a disturbance comes, and there are damages of some wind turbine also. There are some damages of some wind. For one wind turbine, there are some damages that for this of subsystems or even the whole system of one wind turbine. Then in the wind farm, there's a reduction of benefit. So then we need some time for recovery. So in the whole period here is the recovery period, we call it. Then after some recovery period, it's come back to good state. And after some time during the service life, there probably not only one disturbance. There could be 2 or 3 or even more, many disturbances that reduce the capacities or reduce the benefits of the wind turbines in these wind farms. And there are some disturbances, another disturbance come again, then there's a reductions of benefit or service life alive. Then we need some recovery period to be back to good state until the end of service life. So that's the curve for benefit. And also we have another 2 curves. The bottom, the last, this point dash curves here, the blue one actually is the curve for reserve. So we model it. That's the problem that, so in each time step, there's some benefit generated due to the electricity production. And then we put some percent, we could consider as like 60% of the benefit generated by the total wind farms, and then as the reserve. The purpose to have this reserve actually is shown here on this red curve, is the capacity or economic capacity for this wind farm systems, because we accumulate these reserves as the economic capacity. That means when there's some disturbances, we need some capacity to recovery to recover back to the normal state or to good state, then because according to the definition of resilience, we need to use our own ability. The own ability we model as economic capacities we use to support or to finance this recovery event. So that's the red curves. So then you can see that there's some reduction in benefit generation. Then also there's correspondingly, there's some reduction in the generation of reserve. Then here, this reduction of capacity, because we need to fill the gap. We need to support recovery activities. So that means that our capacity reduces or decreases because of this disturbance event. And after that, there's a gradually increase because of this, the save for this reserving. And then after some period of some time, there's another disturbance comes, and we need to use our own economic capacity to recover from this disturbance event. Yeah, so that's we use these three curves to introduce briefly about this. And you can see the gap here, the total area here we can consider is the loss due to the service reduction, or the loss or the reduction of benefit due to also the service reductions. You can see that. And this curve, it's stable, it's horizontal, it's a straight line, because we just for illustrations. You can imagine that because of this activities, or it's because of the power generation by wind turbines and wind farms. So normally it should, the curves not a straight line like this, but should have some fluctuations. So it's the fluctuations of these curves actually depending on wind characteristics, like for example, wind speed and the direction of the wind and the
I lost Jin-Yun.
Me too.
Okay, but he will probably hook up very soon.
Yes. Now he's back.
Yeah. That's good. Jin-Yun, you're muted.
Oh, sorry.
We lost you a couple of slides ago, I think.
Oh, okay. I'm sorry. Now you can see that?
Yep. Yeah. Now we go.
Yes. Oh, yes. Sorry. I start here. You can see that from this figure, you can imagine that the reduction of this benefit due to immediate reduction of the benefit reduction due to these disturbances actually is corresponding to our definition of robustness. And then, and then the length of this recovery period and the area actually is corresponding, or it depends on this preparedness level and adaptive capacities. Yeah. And that's this figure shows the normal definition of our probabilistic resilience modeling, or resilience modeling. The probabilistic is not come out yet. And here we just show, from this figure, we want to show the definition of resilience failure. Actually, when during some, after some period time, there's some bigger, for example, there's some big disturbances, and we need long time, and we also need large, big capacity, economic capacity to support this reduction of benefit, or to support this O&M operation and maintenance activities. But for example, the capacity curve here, the capacity we have until this time, it's not sufficient to support these activities. It's immediate to get down to zero. Then we call it, or we define it as the resilience failure event. And the similar you can imagine as the definition of reliability, or the failure probability, and the probability of safety. We also have the limited state function for this resilience failure, and we define resilience failure as the probability resilience failure based on this limit state function, as the function of this A is decision alternatives, and C here is the ratio we save as the reserve, and the T1, T2 is the time period we consider for this resilience failure event. So that means from 0 to T1, we don't have any resilience failure. So the minimum of this limit state function is larger than 0. But during this period, we have a resilience failure. So minimum value of this limit state function become less than 0. Then that means resilience failure happens in this time interval, T1 to T2, actually. And you can imagine from this the comparison of these two figures, and also you can imagine from the definition of this resilience failure probability. You can imagine, consider this resilience of these wind farm systems. We need to consider the performance of wind farm systems during its good state. But we also need to consider disturbances occurrence as a probabilistic event, and the performance of infrastructure system like wind farms during good state is also a probabilistic problem. And this occurrence of disturbances and the scale, the intensity of this disturbance activities also a probabilistic problem. And the recovery period, how long we need and how much the capacity we need to support this operation and maintenance, it's also a probabilistic problem. And after that, again, it's a probabilistic problem. So we need to use these probabilistic tools to simulate or to consider the variation of the benefit generation of these wind farm systems during the whole lifetime. And we need to then support this resilience modeling. So that's why we call it probabilistic resilience. There are uncertainties, and also there's strong dependencies within these systems. It's that's why we call it probabilistic resilience modeling here. And then I hope to use three simple illustrations to show what's the background, or what's behind we call this resilience informed management of systems. So we have a horizontal axis is this decision alternatives, and we have this vertical axis is resilience. It could be like, for example, 1 minus resilience failure. And then we have this curve of these resilience curves, and then we can set the minimum value of this acceptable resilience. So 1 minus this PRF as this value. Then from this curve, we can identify, or we can define these acceptable decisions or feasible decisions to make these decisions. And further, we not only have this resilience curve, but we also have a benefit curve varied with decision alternatives. Then inside the area of acceptable decisions, we can find the decisions corresponding to the highest benefit we can get. Then we can take these decisions to support this integrated management for these wind farms. Then it's the idea or general idea that's to get this benefit, or to support this according to the benefit curves. We support this identification of decisions. And the last illustration of this purpose is that we now have the curves for resilience and the curves for benefit, but without any extra informations E. But after some time, we have some extra information E, then we can change or update our benefit curves. We can also update our resilience curves. Then you can imagine that from the curves, we don't have any extra information, only just made from our prior knowledge. Then we have the benefit B0 star without any extra E here, like we show here in the second illustration. But we can also have the benefit point or B1 here to make another decision with this extra information. So we also get acceptable decisions with extra information to get the whole area. Then we find within this area, we find the highest benefit point, this benefit with E. Then the difference between these two benefits with extra information and without extra information, we can term it, or we can consider as the value of information. We can measure the value of information of this E depends on the whole idea like this. So that's represent this resilience informed management of this for this general systems. Or even this is also available for wind farm systems. Now, as you can see from last slides on this resilience modeling, actually, the one key point is our understanding of the systems for this offshore wind farms. So we use hierarchical structure to describe this offshore wind farm systems. We consider 4 different subsystems as an integral framework to consider as one big offshore wind farm systems. There are 4 subsystems. The first one here, on the top one, is the management systems. And the second is the environmental systems, and the infrastructure systems, and economic systems. If we consider offshore wind farm as one large-scale integrated systems, then these 4 systems you can consider as subsystems. For the management systems, actually the aim is to manage the offshore wind farm system efficiently to ensure the sufficient power generation to maximize the benefits and also to improve resilience and sustainability. So here shows some terms we would like to introduce it. One thing important thing I forgot to point out that these 4 subsystems actually are interconnected. So not only top down, but also bottom up actually to support finally the management. You can imagine that the wind farms, especially the offshore wind farms, subject to very complex exposures and hazards and operational loads actually are 2 main causes of these failures of systems, component failures. But it's special for wind structures that wind characteristics determine the energy production, but also wind, especially the strong wind, is the causes for failures. But the small wind, not strong, very strong wind also may cause fatigue and the structural deterioration. Yeah. And for infrastructure systems, we consider as interdependent systems. So we have here just illustrate 3 levels, component subsystem levels, wind turbine levels, and also the whole farm levels. And in each level, they are interconnected. And the failure event, actually, you can imagine there's 2 different phases. The first is initiation phases. When there are some disturbances, there are direct damages of some components or even some wind turbine structure systems. And then after that, there's some propagation, there's some redistribution load, and also they are because of their interconnections or interactions. So they are cascading failures. That's our whole idea about the infrastructure systems. And the last here, on the bottom is the economic systems. So the infrastructure systems have produce this wind energy to generate wind power, but then transport it to shore and finally convert into this benefit. Yeah, I hope I still have some minutes, and I would fast introduce the examples. You may find details in these papers, journal papers we recently published in this applied energy. We consider one wind farm located in Zhanjiang. It's in southeastern China. We consider in the environmental system, we consider typhoon events. It's a big hazard. It's as a portion process. And because of its offshore systems, we consider turbulent winds and irregular waves as coupling events, and also we consider as it's a random process. And in these management decisions, we consider different indicators, for example, or scenarios with different target design reliability, with different levels of preparedness and different numbers of wind turbines, and the percentage, C, as I presented above in the previously, that the percentage we save from the benefit to accumulate it for these economic capacities. Then we have the physical properties we listed for these wind turbines. So it's listed here. Then we consider it's the failure events. For structural components, we use structural analysis, typical traditional structural analysis, but taking these uncertainties into account. For these mechanical and electrical components failure events, we model as a homogeneous Poisson process, but we also consider as a cascading event, so they are interconnected. You can see the details in this journal papers. And then for these economic systems, we have a material cost for this O&M activities, and we also have a labor and transportation cost. And we consider this in energy production as the benefit. And I showed that curves like this is changed with wind characteristics during good state when the wind turbine, but during the downtime, then we also model the recovery period as a probabilistic event. Yeah, so that's the economic system we modeling. We consider 6 different scenarios with 3 different levels of failure rates and also of these components, and also different definitions of the probabilistic model of this preparedness level for this repair event activities, and for this recovery preparedness level, and also the repair time for different components. So we consider 6 different scenarios as shown here. And we actually can have many outputs. Here just show some parts of the outputs. We can have this resilience failure as the function of time, and also as the function of different values of this C is important for this reserve, and especially for this economic capacities. We also have this curves for probability of resilience failure, value time with different lambda as an indicator for the failure rates of the pitch system and the gearbox failure rate. And we also have we can also produce the curves from this resilience modeling framework, that the resilience failure probability changes with different value of C and also different number of wind turbines we decide for these wind farms. You can see that. And also in our another papers or academic papers, that we can also have potential outputs from this probabilistic resilience modeling. For example, like expect value of the total benefits. So it's not only expect value actually you can measure, it's also the benefits variations during the whole service life. And also we can have the reliability of energy provision. For example, the downtimes, the length, the total length of downtimes during the service life. And we can also, another interesting indicator is, or useful indicator is stock keeping for different types of subsystems in the failure state, simultaneous state, because that's the stock keeping. You can find the details in these papers. Yeah, thank you for your patience. And in this conclusions, actually, you can see that from our proposal of this probabilistic resilience modeling framework, we realize integrated management of this such large, typical large scale, but also complicated systems, offshore wind farms. Actually, we realize it's integrated management quantitatively. The model of wind turbine as a system of systems, and the system representation of wind farms with different, actually several different levels of dependencies. And we also capture all the uncertainties we can take into account associated with this performance of wind turbines, and also the damages of different types of subsystems. And the last is we are able actually to enhance the integrated management of these offshore wind farms from within this our resilience modeling framework. For example, as you can see from the examples, that benefit estimations and the design reliability of the components, and also stock keeping. Here, just the main references to support our this recent the research work in this recent years. And the last, before my ending, actually, I would like to introduce briefly of ongoing research group, my research group at Shanghai Jiao Tong University recently. That, for example, the first is extreme disaster analysis I did in the last years. Actually, we hope to identify, actually, we already presented the different attributes of low-tail subsets and the high-tail subsets and the non-tail subsets. So it's a book, and they have actually different attributes, different size, and also they have different values. But actually, normally, if you can see in this probabilistic model for this disaster or natural hazards indicators, normally they are ignored, or they are not derived theoretically. There's some problems in this probabilistic modeling. So we hope to provide this accurate probabilistic model based on the identification of this discrepancies, because ignoration of this low-tail subset and high or high-tail subsets, these attributes, might cause big problems because their corresponding consequences are really high. If you consider the risk definition, it's probability multiplied by consequences. So that's the main idea of behind this study. And recently we introduced AI, this technology to support, also to integrate with traditional probabilistic model to support this analysis. And the last two I would like to share is, the first is the carbon emissions analysis. Now I'm doing with some postgraduate students on this offshore wind turbines and offshore wind farms. Actually, we hope to not only limit to the cradle to gate, but also cradle to the end of the life. So the complete study to of different materials and also for the whole wind turbines. And we hope to consider different uncertainties, and the last aim, or the final aim, actually to integrate into decision support or management, this management of this offshore wind turbines and wind farms. We have some simple work already about this relevant to this. Actually, it's a small step actually just to introduce one indicator as the trade-off between the carbon emission and also the performance, for example, seismic performance of engineered structures, to make this indicator and to support to realize it in engineering decision making. And the last thing, I just have the general idea, and we are now starting, is about the probabilistic digital twin for this offshore wind turbines. The whole idea is to make this cycling between this probabilistic modeling and integrated management, and the real offshore wind turbines. For example, the health monitoring and inspection and maintenance. It's a dynamic process, and it's a cycling process like this. So that's the last thing I want to share. And finally, before the end of as a part of the organization, I would like to show the left webinars, and all of you are welcome to join this great event. I think all presented in the future, I think very good and very well-known these scholars in the world. Yeah, that's the end of my presentation, and thank you for your attention.
Thank you so much, Jin-Yun. And now we still have some time for questions, and I'm looking in the chat here.
Yeah.
There is one from Benjamin Schmidt. Let me just scroll down here. Well, I can also just make it big. So Benjamin is asking, how do you capture the dependency of different extreme events? For instance, storm and extreme sea state. keyword tail dependency in your work. Finding a common model for instance sea state characteristics and other climatic aspects seems to be difficult due to the complex nature. The available data and records of, in instance, wave heights and periods also in connection with other events are probably often difficult to capture.
Yeah, I think it's a very good question. Actually, it's a tough task. Honestly, our present work is only about these tail extreme events, only limited now to the single hazards. But actually, we also interested about it's a good point that we have to consider the coupling of different extreme events. Like you mentioned, this storm and sea states. It's but it's difficult, I understand, because even the available events or available data are very less. But we have already start some work for some mountain area about this for this landslides and these things like earthquake and flooding. But yeah, it's a tough year. Thank you for the question. I think it's a good point. It's a difficult task. I agree. And also one thing I want to point is it's not only, it's not why I say tough, because it's not only probabilistic problem, because it's also special, not only time variant, but it's also special problem because the extreme events also happens within some special areas. So it's also, that's why I think it's a tough work. Yeah, the second one is.
So Benjamin says, thank you. Dagang is asking, are there interdependencies among the wind turbines in a farm? How do you consider them if there are the interdependencies?
Yes, thank you, Professor. Actually, I think I'm, because I saw the time problem, I didn't present clearly about, for example, in our examples. Actually, we consider this interdependencies in these examples, for example, in our system representations, because we consider the physical properties, they are dependent on each other, and also the failure events, they are interconnected, or they are dependent on each other. But also the hazards, they might be different on different wind turbines, but probabilistically they are interconnected. So when we represent as a whole, as a system, so we have different levels of dependencies we consider in these wind farms.
Right.
Yeah.
Please, now is a good time to ask.
Yeah.
Of course, if something comes into your mind at a later point in time, also if some of you are reading the literature indicated by Jinjun, you're always welcome to write directly to Jinjun for any clarification. And maybe also help to find some of the publications.
Hi, I have a question, Dr. Qin. I see you modeled the resilience or the performance as a deterministic horizontal line in your presentation. And do you consider the whole benefit also as a probabilistic problem, or is there any possibility that a disturbance will actually increase the performance or the benefit? Or the benefit here you refer to as the full capacity of the structure? Thank you.
Yes, thank you for your nice question. Actually, this curves I present here is only for illustration purpose, as I introduced during my presentation, but because of loss of my screen sharing during that point, I think because we consider the performance of infrastructures during good states is a probabilistic event, probabilistically, sorry, and the occurrence of disturbances and the length of the recovery period also probabilistically we consider, and then the numbers of disturbances during the life period, service life, are also probabilistic. So all things actually are probabilistical. So that's why here is only one curve for the benefit evolution during the service life. But actually, when we do this resilience analysis or resilience assessment, actually we generate millions actually of these curves to analyze this, to simulate the performance or to simulate the benefit evolution during the whole service life. So it's a full holistic model.
In this way, what we see here on the screen, it's just one realization out of millions, which are generated by Monte Carlo, right?
Yes. Yes. There's one question I saw.
Did that answer your question?
Yeah, it answers my question, because I was thinking in the end, it is uncertainty that we are dealing with. So I was thinking the benefit or the performance of the facility might also be probabilistic. And here I saw horizontal deterministic lines. So that, yeah, it answered my question. Thank you.
Super.
Yeah, thank you. I saw one more question from the chat box from Dr. Qing also. This about this computational, sorry, this cost with temporal and spatial modeling of this iPhone and these things. I would like to explain like this in our past research work. For example, this journal papers headed by Ming Liu. Actually, we introduce actually big data technology to reduce the computational cost, or to simplify not simplify, but to make this calculation efficient. But now we are working actually using more advanced this AI technology to solve the problem. You are right. There's a huge, or they are large, this computational cost. When you read if you read the paper, you can find we use some simple but useful this big data technology actually to solve this this computational problem. I hope it's the problem is answered. Yes. Another, what's the role of vision in proposed digital twin? Oh, this, yeah, thank you for your.
Hello, Professor Qing. I have a small question.
Hello.
Can you hear me?
Yes.
From the structural point of view, you defined the capacity of the structure, and also this hazards are all probabilistic. So the failure of the structure is also there's a probability. And my question is, how was the capacity or the performance of the structure defined? I mean, use the displacement or the internal forces, for example. How do you define whether the structure fail or not? And this is my question.
Yeah, it's a point. We define actually the structure, not the structure, actually the failure of different components, different types of components. Actually, we consider structural components failures, like a tower or these things. Like as you mentioned, we use displacement or even the tolerant stress. These things to consider the failure or not failure of these structural components. But there's also two different another types of these components, like mechanical and electrical components. Here for these two categories, we model these failures as a homogeneous Poisson process HPP. Actually, this is consistent with the with normal research study on this mechanical and electrical components. Yeah, that's
okay. Thanks.
that's the idea. Yeah, thank you. Yeah. There's one question for Bayesian in for this Jingshen. I didn't see the full name. Sorry, the Jingshen's name. Jingshen's question is about the Bayesian analysis. Yeah, actually, we already have some Bayesian approach used in this probabilistic resilience modeling, actually. And in this digital twin, I think because of we have to apply the Bayesian. Sorry, my computer didn't. Sorry, my computer looks. Can you hear me?
Yep.
Oh yeah. So my computer doesn't work. Sorry. Because of in this digital twin, actually, like I showed just now, there's a interaction between this probabilistic model and the integrated management and the real offshore structures. We get the data from health monitoring and these things. We have to apply the Bayesian analysis. Yes, I think. Yeah, I think that's the whole idea. Yes.
Okay.
There's another question.
Yeah. But time is also running out.
Yeah, just my quick response is that the number increases. Yeah, it's a. So we're now working using this. We hope to use AI technology to solve this problem. That's true for probabilistic modeling of resilience modeling. The computational cost is a big problem, but we solve it in these examples. But we want to try some more advanced and more efficient.
If I may add maybe an idea to this. So when we use big data analysis and we have these huge amount of simulations, then we can also identify by classification schemes which domains of realizations from the Monte Carlo simulations are contributing to the different types of consequences which we are trying to model. When we have identified these domains, then it becomes quite obvious that you can take benefit from intelligent sample schemes or Monte Carlo techniques like the subset, where you just direct the sampling to those identified particular interesting regions where there may not be so many realizations, but then you can fill up efficiently with realizations in those domains which really matter.
Yeah.
Okay, ladies and gentlemen, I think this was, thank you so much, Jin-Yoon. I congratulate you with a very nice presentation, and thank you to the audience for being here, and thank you so much for the super good questions. So as Wei-Heng is putting into the chat, the next lecture will be on September 26th. There's also the link to the ACSS homepage where more information can be found. But the presenter is Paolo Gardoni, and I'm sure that you will be thrilled to hear what he has to say. So with this, I want to thank you again. I wish you a nice evening, afternoon, morning, night, wherever you are. And I look forward to see you again very soon. Thank you.
Thank you all. Yes.